I think it's become clear from the whole discussion so far that this whole digital transformation journey is taking center stage within the construction sector. I mean, there are reports upon reports upon reports that discuss that. This is just one example last year from McKinsey talking about the potential for disruption of the digitalization of construction products. And in fact, that this is happening now within the next 1 to 5 years. But actually, this was with data before the pandemic. Because if you add the pandemic on top of that, that has actually operated as a digital transformation catalyst, with companies accelerating their digital transformation journey and achieving targets that they would normally do in 2 to 5 years in just a few months. So I think that makes this an even more pressing and important topic, that we need to basically create the frameworks necessary to help our industry move forward even faster than we thought would be necessary just even a year ago. On that, digital twins, in my view, are at the core of this digital transformation journey. And I think you've already seen from the presentations before us about what the value is. I mean, there's clearly quite a lot of potential value across all KPIs: cost, time, quality, safety, sustainability, resilience, and so on. But then the key question that comes to my mind is, if digital twins are so great, why aren't they as ubiquitous as physical twins? Why don't we have them everywhere? And my tentative answer is these 4 main bullets. The first one is, we know the physical twin as a product, but we're still discovering the digital twin as a product. And we need a lot more R&D to get to the point where we would have a similar degree of understanding of digital twins as we have of the physical assets, the bridges, the buildings, the roads, and so on. The second aspect is that, likewise, we know and we have been automating for decades now physical twin processes, design processes, construction, maintenance, and operation processes of the physical twin. But we haven't done that for the digital twin. Ways to design the digital twin, construct the digital twin, the twinning process, maintaining the digital twin, and so on. That is primarily mostly manual, therefore perceived as very expensive. Therefore, the value to cost, the benefit to cost relationship is just not there in place yet to allow us to penetrate the market quite fast. So again, a very big need for R&D to create more AI and automation to help the twinning process. The next 2 are more industry related. One has to do with the fact that owners have quite a lot of experience of the value of physical twins, but not of digital twins. And that makes there a very big need for real use cases that can help push for much more rapid market penetration. The last but not least, I know it's a bit controversial, but I think it's the reality, is that vendors throughout the industry are looking to catch on to the digital twins wave without actually doing the work. We are looking one after another, BIM products coming out with slight enhancements, being relabeled into a digital twin product, and as a result, accelerating digital twins as a concept into the trough of disillusionment, which will take us quite a long time afterwards to bring it out of that trough and back into popularity. So how do we solve this problem? Well, on that space, at least at Cambridge and also with colleagues like Raphael Sachs and others, we're trying to do as much as we can on those first 2 bullets to understand the product and understand the processes necessary so that we can service the market better. On the first bit, on understanding the product, a year ago, we published a paper with Raphael Sachs where this figure comes from, although this one is slightly adapted since last year, that sort of gives you an overview of the relationship between digital and physical twins. We like to use here the paradigm of a person standing in front of a lake. the person being the physical twin, and then underneath him, his reflection on the lake is the digital twin. So you see the positive axis going up is the physical product and process, and the negative axis is the information volume. And so starting from the beginning of time, you have your planning and your design phases from the moment of conception. On the physical end, you have all your design processes going on. And then on the digital end, you have the outcome, which is the design phase, product and process information gradually taking place. This is what we would call the design phase digital twin, or the fetal stage digital twin, before the building is actually born. At the birth time, that's when prefabrication starts, which means construction processes start, prefabricated parts start happening. And on the other end of the spectrum, on the information end, you have construction phase product and process information starting to materialize. And then continuing on beyond the weaning phase, when the prefab parts leave the mothership and go to the actual site for installation, which is where you would actually grow your child physical twin into an adult. And at that point, that's when you've reached your project handover stage, maturation, where you have your adult physical twin. And from that point on, theoretically, you are operating it. You have operation processes that are producing operation phase product and process info into the operation phase or adult digital twin. So one of the other reasons I like this figure quite a lot is that it helps us understand from a popular perspective, a digital twin as opposed to a building information model. So the most common perception of a building information model is the thing an architect would give you. And that thing is basically this little yellow line you see there, okay? It is the as-designed building information model at a point in time, let's say times T1, and that's just that little yellow line there, without containing any previous information about how you got to that point or anything else beyond the design data. Now, if I was to extend that a bit further, I would perhaps get your design status model that includes your design phase process information at times T1. Or further beyond that, you would get your as-built building information model containing the construction phase product information. Or going further than that, you'd get, as Rafael was explaining before, the project status model at times T1, which includes the construction phase process information. And that's why we have a problem today, because we have all of these different models, all of them trying to help us understand what's going on with our buildings, hoping to be exchanging data across them, rather than thinking that, well, actually, all of this should be put together somehow. It doesn't matter if it's in a federated format or in another format, but it should be the same graph platform supporting them in the back. And let's say temporarily, we can call that the n-dimensional building information model at times T1. I would still not call that a digital twin yet. What I would call a digital twin is what you see here. It is that information plus any previous value of that information since the beginning of time for that particular asset. The reason I think this is very important, I'll just give you one example. Let's say that at the operation phase, a pipe fails, and you want to do some forensic analysis to understand why did the pipe fail. You'd like to know at that point, what was the history behind the pipe, how its dimensions changed, how its materials changed over time, why certain decisions were made and why not. Because oftentimes it is within those decisions you understand why something actually occurred, so you can avoid having that problem in the future. So having said that, some other important suggestions of my own is that I don't think digital twins should have any data in them. I cannot stress that in more stronger terms. Data have no place in a digital twin. Information does. Data is just raw data that may or may not have any information value. And it should be there to help us derive the, let's call it the level 1 most basic information level digital twin coming out of structured and unstructured data, typically held separately and deleted after use. Things like point clouds, things like images, none of that should be, in my view, in a model. Again, though, that would be a very basic digital twin. As through the examples that were presented earlier, what we want to achieve is process that information, look at the information patterns, interpolate, and generate knowledge. And then beyond that, take those knowledge patterns, do some simulations, extrapolate, and as a consequence, generate insight. I think that's when we're going to get the best value out of digital twins. And by the way, to do any of those things, that is actually a perfect use for AI. And that's why the journey of digital twins is inseparable from the journey of AI. One helps the other actually quite well. So this is the journey that we've embarked at Cambridge, both the Center for Digital Britain, focusing a lot more on the adoption of standards and defining the digital twins journey at the policy level, as well as my own group that focuses a lot more on can we actually build these things somehow effectively. And like I said, we can't derive insight without knowledge, and we cannot derive knowledge without information. So we have to start at the beginning. We have to generate information level digital twins from structured and unstructured data. And a lot of our work has focused on unstructured data, in particular, things like points and pixels and thermals, because that is in fact a very big challenge. On that space, we've done a lot of work on using basic things like points and pixels on any asset, a bridge, a building, a road, and then from those points and pixels automatically generating the components, registering the textures on top, and then on those textures trying to derive information such as things like condition information and other things that might be of use later. And to do that, we've come up with multiple methods, such as this one, mid-range mobile videogrammetry, allowing us to extract raw geometry from just a mobile phone from 25 meters away with a sub-centimeter spatial error, taking those point clouds, equalizing the densities, fixing the holes, producing generally good quality data sets that are meant for the machine's eyes to see. I want to make that very clear. This is not for the human's eyes to see, because the main purpose is to process that into this level 1 information stage digital twin. That is a big problem on its own. There's been reports upon reports that talk about for every 1 day of laser scanning, people have to spend 10 days modeling. That we are working with point clouds with well over 30 billion points in many cases. And most importantly, it's a very boring job. Imagine someone tried to model pipe after pipe, valve after valve. I mean, the example I have here on the right, this reactor building, 40 billion points. It took 10 people 6 months to make one model. I mean, this is clearly a case that screams for automation. In that regard, we've come up with several methods to help us achieve that completely automatically for bridges in the first instance, where everything is exposed and the number of topologies is small, but at the same time capturing the real world skews and peculiarities of every component, going from this stage, the points and the pixels, into the detected components, and then from the detected components into the actual model outcome. And we've done the same for buildings, trying to capture raw data, converting that to usable information, creating the object-oriented model of that process, going from the point cloud into detecting the rooms and the floors, and then from the rooms detecting floors and ceilings in the presence of clutter, detecting the walls, fitting the components, and creating the actual model. We've recently done the same for industrial facilities together with Aviva and BP, capturing cylinders, elbows, channels, I-beams, valves, flanges, and so on. A pure deep learning application, which can then be enhanced with contextual information to give us a high quality model at the end of the process. Once we've done that, we can then enrich that with additional information coming from the textures, such as condition information, cracks and spalling and patching and other problems. We've done that for bridges already, where we're capturing quite a large number of defects and their properties and putting them back into the model. And we've also done that for roads, where we're able to capture cracks and potholes and patches and rutting and shoving, measuring that information and bringing that back into the digital twin of the asset. We've also brought in sensor data back into the model to create the connection effect that was discussed earlier today, by modeling the sensors on the components and then bringing the time series data for the connection so that we can see exactly what is happening, in this case from a structural perspective, on our asset as our asset is being used. This is the long-term vision. Basically, how can I achieve real-time monitoring and operation of assets through digital twins, not only at the single asset scale, but at a portfolio of assets and eventually at the system of systems level, like Raphael Sachs was explaining earlier. That's the dream of the National Digital Twin that the Center for Digital Build Britain has been focusing on. On that, we're working on several existing projects, some of which were mentioned already. This one called Cloud Building Information Modeling, that's focused on generating geometry, enriching the product, modeling the processes, and then running applications on top of that. The BIM to Twin that Raphael was explaining earlier, I won't explain that as it was already mentioned before. And also another one called Omicron, which is focusing on doing similar things to the BIM to Twin project only for roads, going from a road digital twin to decision support tools, to smart construction interventions, back to inspection and back to the twin. So this would be a plan, do, check, act cycle, exactly as Raphael was explaining earlier. Our long-term vision is that eventually we should get to a point where we are looking at assets as a combination of their digital and physical forms, where in the physical versus digital and product versus process scales, we can then combine smart materials in the physical product, automation and robotics in the physical process, data science under the digital process, and digital twins under the digital product. And in doing so, I think we can run our assets a lot better into the future. That's all I have for you. If you want to know more, we published a book recently that covers a lot of these topics. You're welcome to take a look at it. And I just want to thank the people who did a lot of the work that you saw today, as well as the sponsors who funded it. And thank you very much.
Thank you very much, Ioannis. Now I understand the Brexit, and we have to ask for a Spanish seat, something like this, in order to make such kind of work as you are making with the CDBB and the university. I think this is extraordinary. And what you show us is something very interesting, because it's not only talking about the building part of the digital twin, but also the infrastructure part of that. And this automation that you are showing us right now is really interesting.
This is just an example, by the way. This is part of our software called Gygax. Gygax is available for free on GitHub. Anyone can download, it's open source, and you can try to work on that. It gives you the ability to play with point clouds, with images, with IFCs, with various other data sets, bring them together, and manage to go from data into usable information within this environment. Yeah. So I'll stop sharing now.